Hybrid Composite Beam, HCB, is a new and innovative beam design that was developed as an alternative to conventional concrete and steel beams currently and historically used in bridge construction. The beam consists of three main subcomponents: a fiber-reinforced plastic shell, compression reinforcement, and tension reinforcement. The compression reinforcement consists of self-consolidated concrete that's pumped into an arch conduit within the beam shell. The tension reinforcement consists of high-strength steel pre-stressing strands, untensioned, that run along the bottom flanges of the beam shell. All of this is encapsulated in a fiber-reinforced plastic shell protecting the beam from salt-induced corrosion and providing added structural capacity. The result is a bridge framing member that's simple to design, manufacture, and construct, and that's cost competitive with conventional beam systems. In addition, extensive fatigue testing shows significantly better performance than design code requirements. The beam system has a reduced carbon footprint, using 80% less cement, one of the largest contributors to the carbon footprint, than conventional concrete beams of comparable application. Implementation of the HCB system will also reduce traffic disruption and congestion, since its lighter design requires less delivery and erection time, thus providing for quicker installation. With the FRP shell, there's no painting requirement, no rusting, cracking, or spalling, thus resulting in a more sustainable product that will provide 100+ years of service life. The hybrid composite beam can be erected in the same manner as pre-stressed concrete or steel beams, but with smaller equipment due to the lighter weight. Prior to injecting the compression reinforcing, the self-weight of an HCB is approximately 1/3 that of a steel beam and 1/10 that of a pre-stressed concrete beam having the same strength and stiffness. This results in a net savings in shipping and erection costs. 6 HCBs can be hauled to a site on one truck, where it would take 6 trucks to haul a comparable concrete beam. When used in rail applications, these beams can be handled with the railroad's own rail-mounted lifting equipment. This reduces both time and cost in placing or replacing a rail bridge beam that would have required a separate but much larger piece of lifting equipment than is in the railroad inventory. Once filled with concrete, the HCB has essentially the same mass as an equivalent steel beam, which is also desirable from the standpoint of dynamic behavior. The combination of an efficient use of steel, concrete, and FRB, coupled with the lightweight characteristics of the HCB, results in a cost-effective application of FRP in a structural member. The HCB also provides flexibility in construction, in that there are basically 3 methods of deployment that vary depending on project requirements related to weight and speed of installation. For projects where the weight advantage is more desirable, the HCB is installed as an empty shell and subsequently filled with concrete, with the HCB shell serving as a stay-in-place form. In the next level up, the arch concrete for the HCB can be pre-filled and the beam can be erected as a true hybrid composite that supports the deck casting. In the next level up, the arch concrete for the HCB can be pre-filled and the beam can be erected as a true hybrid composite that supports the deck casting. Where speed of erection is the most important criteria, such as in accelerated bridge construction, ABC, the arch concrete is precast in advance. Preferably, this would be done in a precast yard or staging area that would allow for HCBs to be set up to the geometry consistent with the final erected cross slopes and super elevation transitions. At this point, the concrete deck is checkerboard cast with either longitudinal match cast joints or small sections of omitted concrete that allow for cast-in-place closures after the units are erected. This final erection sequence can result in the ability to install and open a bridge superstructure in as little as 1 day. John Hillman is responsible for the original idea and the concept of the hybrid composite beam system, developing the first prototype in 1996. Satisfying both professional and personal curiosity, Hillman studied the historical development of structural systems such as reinforced concrete, pre-stressed concrete, and general innovative bridge design, and concluded there were opportunities for structural innovations that could reduce costs and address environmental and sustainability concerns. Mr. Michael Zicko is credited with development of the manufacturing technology and construction techniques.